Hello, my name is Andy Aquila. I'm one of the instrument scientists here at LCLS. I'm in charge of the tender X-ray instrument, and I'd like to give you an introduction to imaging, or X-ray imaging, and a little bit of information about the tender X-ray instrument. So, as a refresher, you may remember that we wanted to find a numerical aperture of a lens, and this is useful for a lot of characterizations of what resolution you have, what depth of focus you have. And that's just effectively the diameter of the lens over twice the focal length. And that is what we define as a numerical aperture. This concept comes up often. You may hear of an f-stop number if you're ever into photography, and numerical aperture is approximately 1/2 f-stop number. And why is this useful? Well, if we wanted to image something, a standard microscope setup, we have a light source, we have some condenser optic, which illuminates a sample, which has a certain depth of focus where we actually can focus on the sample. Then we have an object and image distance, and we re-image, usually magnify the object onto an image plane with a CCD or your eyeball. And the depth of focus is approximately 1/2 lambda over NA squared. With magnification of the object, how far you can see is the distance of the lens is from the image screen, divided by the distance of the sample to the lens, and that is how magnification is. But the resolution is effectively equal to 1.22 lambda over the numerical aperture. So it really depends on the size of the lens. You can't do this with any ordinary lens, and it also depends on the illumination light coming in. You'll notice it comes as scales as lambda, which is important because if you really want to get to atomic resolution, which is one of the reasons we go to X-ray, is the reason we go to X-rays, to get to this atomic resolution. And these are the very basic equations you'll see in any optics textbook, and they apply equally well to X-rays, except we don't really have good lenses for X-rays. X-rays are very materials are very transmissive or transparent to almost everything, unless it's a very high Z or high atomic number material. But we can make diffractive optics. And these are Fresnel zone plates or Fresnel lenses, or just zone plates. And what they do is, you can think of interference effect, where it's effectively a grating running across, but it's a grating that changes its period as a function of position. And you can think of the light coming into this, and any clear zone, you can actually say, okay, I have a focal point in the center of the central symmetric focal point, how many wavelengths it is to get from ring 1 center to there. And then I block it when it's a half wavelength, and I sum it when it's and I let light in when it's a full wavelength. So it always adds constructively interferes. And we can actually calculate these equations, and we can figure out the bandwidth, depth of focus, and effectively make these out of gold or other materials where you have high Z absorption and maybe silicon or diamond transmissive. And these are 3 little zone plates here. We use it at FEL for focusing. I've used in the past. They actually have 100 nanometer outer zone width. But you'll notice this is a clip and a very small screw head, actually. So these are very small optics. So the problem with using them at FELs is you have to be very close to your sample. And why is that a problem? Well, at synchrotrons, that's not a problem. You actually end up with, this is XM2 at the advanced light source. Beautiful cellular imaging where they actually cryo-freeze cells and actually can section organelles and do 3-dimensional tomography on cells with 50 nanometer resolution. If we try that, here's a zone plate that went into the beam. Here's a zone plate after. Unfortunately, we have a lot of fluence, and that will actually physically melt the object. These are also not exceedingly efficient. They're typically 10% efficient in soft tender X-rays. Above 10 keV, we can make them more efficient by, instead of being absorbative devices, we can make it a phase device, and that'll make up to 30% efficient. But all in all, while they have good resolution, which is proportional to outermost zone width, and hence the numerical aperture is proportional to outermost zone width, you end up, which is on the 15 to 25 nanometer scale, you end up in a situation where these lenses don't work so well for FELs. We typically use other optics, and we use them for focusing, not necessarily for imaging. And these are called compact or compound refractive lenses, and they're usually made of beryllium because it's very low Z, and this means they get a high efficiency in the X-ray range. They're not so useful below 5 keV because they absorb a lot there. But once again, these are very small objects, but you can use them in synchrotrons as imaging objects, and they do have some aberrations. But you can fix that. But they actually do a reasonable job. And the interesting thing is, if you look at a cutout of these, they look like a divergent lens. And the reason for that is fairly simple. The index of refraction is slightly less than 1 for X-rays. So they will actually act as a convergent lens in X-rays, even though they look like a divergent lens for visible light. Everything is kind of reversed when it comes to X-rays because of this effect. And the first time they tested these, they just took a piece of aluminum and drilled holes into it with the repeating pattern, and sure enough, it did actually focus. And these are used often at LCLS. Most of the hard X-ray instruments actually have beryllium lenses or compound reflective lenses as their focusing element. So then, if we can't use lenses or any other things to actually make a real space image, then how do we actually make images? You've probably gotten a chest X-ray or a dental X-ray. You know we can actually make images. And the answer is we have an X-ray tube. This one is actually taken directly from Compton's paper that I scanned in. And you have a little aperture here. And you have your object, and you can actually just project it with the aperture. The rays go out straight. You can actually do ray tracing. And you have a magnification that is proportional to the distance L0 and L1, how far you're away from your object to your and how far away you are to your film. Typically for like dental X-rays or a chest or an arm X-ray, the film is right there. It's fairly close, and the resolution is effectively proportional to your aperture size or pinhole size that you use, times the with some caveats of magnification. Now, can we get away with this? Well, let's say we wanted to have a slightly sub-millimeter resolution. So let's say we use a pinhole that's 500 microns. We would actually have to go pretty far to get into the limit where we actually worry about diffraction. And I'm talking about kilometers here. And even at 2 kilometers, depending on your pixel size, because you actually have pixels, not just film anymore, where it's point sources, but you actually have pixels of a certain size, we'd actually be pretty hard pressed to actually get to it where we actually worry for a 500 micron pinhole, where we worry a lot about what the diffraction is doing. Now we can shrink this down to 1 micron, and then you can think about this coming in a lot closer. And you can actually think about when we shrink it down to atomic, yes, we have to worry about diffraction, and we'll get to that. But how does tomography work? How do they do those awesome CT scans? Well, we can do this in 2 dimensions very easily. We just thinking about how optics work, or how it works, we can break the object down into the voxels. I just coded here 16 voxels 4x4 with different index refractions or different absorptions. And we can actually have the beam come and figure out what the intensity is going through them. We can go through, that gives us 4 equations and still 16 unknowns. Well, we can choose a different angle of the light coming in to get now 8 equations and still 16 unknowns. And we can repeat this and repeat this until we sum up all the equations and have enough equations to solve all the unknowns and get what the intensity is in each of these little voxels or boxes. And this is sure enough how they do it for your CT scan. You have a little scanner with a point detector, and it scans across in 1D, and then it rotates, does it again and again and again, and then it travels down the body. That's why you have to sit still for so long. This guy actually got the Nobel Prize in Medicine in 1979. A physicist and a biologist. Interestingly enough, since I'm a physicist, Alan Korkmaz, he was actually doing this on a sabbatical. He did these calculations and kind of forgot about it for many years until he won the Nobel Prize, because he was actually, that wasn't what his primary focus was. This is a picture of one of the first CT scans where you actually see the numbers in the boxes, where they actually did a printout of the boxes. It's very fascinating, the history of this subject. But we're not here for that. We're here for sigmatrons and FELs, mostly FELs. So can we use the same technique? And we do. It's this is actually from MEC Matter Under Extreme Conditions paper, where the focus, they use those CRLs I was telling you about to focus the beam to a very small point, and they put a sample downstream of that focus and propagate. This is considered phase contrast imaging. And why do they consider it phase contrast? Well, the object, it doesn't absorb very much. So what actually happens most of the time, because how the index refraction, the imaginary part is small, the real part actually just gives us a 1 over lambda squared times a constant. And this is usually bigger. So your real part is less than 1, and it can be considered almost real. So you end up with edge enhancements, and these edges, as I said, the beams diverge exactly the opposite what you would think they should, because index refraction is less than 1. And you end up with more photons in some areas and less photons in other areas. And this tells you effectively the refraction or the phase of the object if you assume certain conditions on the phase, assuming the entire object's same density. So you can actually look at shocks and other things. We do this MEC all the time in a single shot manner. What's done at synchrotrons and not really done here at FELs is scanning transmission X-ray microscopy, where they actually make a very small point, and they raster scan that across a sample, and they actually move the sample around. And they have some intensity monitors either in transmission mode or scattering mode, and they actually record the position and the intensity of those. And this is how they did it for a very long time, until we actually got really cheap and large detectors that could actually do CCDs that could run really fast. And this is actually one of my favorite papers. This is a technique called tychography, where they actually take STIXM, but they actually image the like scanning like phase contrast imaging, image the what's in the beam, and sometimes actually if you see outside the beam, and they take that diffraction data and they were able to stitch together by rastering the sample, and they get enough information to actually reconstruct what the beam looks like, but also what the sample looks like. And this one they use an Eiger detector, one of the newer X-ray detectors, but the sample itself is actually one of the reasons I like this, because it's so meta, is an Eiger chip. They actually took a chip for an X-ray detector and used that to raster, so they actually can show what the circuitry was on the chip as an image of how the chip actually worked, which is kind of very meta and very funny. Showing you how the chip works while also demonstrating that it actually works really well. That leads us to the area where we're trying to improve things at LCLS. And that is resolution. While this Eiger and this chip can get really high resolution, you see it's 50 microns, and you can actually really zoom in, it doesn't work so well for biological objects. And the reason for that is you're going to end up with a dose limit. This actually was known since the 70s, and where they predicted it, but it's been known even more recently, where we actually can collect data and actually show this, and show where this dose limit is. And that what happens is the amount of X-rays you need to actually image to a certain resolution goes up. So you have to dose a sample higher to get that resolution. The problem is the sample has a tolerable dose where it actually starts to change as you increase the dose. And at somewhere around 10 nanometers, depending on the sample and how it absorbs, you end up hitting a wall where you cannot actually image beyond about 10 nanometers without actually causing enough dose to, even for a frozen sample, to destroy the resolution at 10 nanometers. Now, this paper is actually was interesting because it highlighted that electrons can do a little bit better, mostly because electron scattering is stronger than X-rays. And they also had an interesting caveat, even in the 70s, saying if you could actually dose within the vibrational period, you might be able to get around this. So you have to you dose your sample really fast with a lot of X-rays. And sure enough, this is what we're planning on doing, and we've done in the past. And this is called coherent diffractive imaging, or single particle imaging. And we move the sample to the focus. We kind of ignore the data in the focus itself, or the collimated beam, and look at the data outside. And this is all scattering, high angle scattering, and it's related because the object is smaller than the beam and it's 2 dimensions. We actually have enough information to reconstruct based on the diffraction pattern alone, which looks nothing like the object, what the object looks like, using methods called iterative phase retrieval. And we can, in the coherent beam, we can write the equations of how the intensity at one plane corresponds to the intensity of another plane, and it effectively is a Fourier transform. So we can actually iteratively figure out what the sample looks like based on the equations of how wave propagation works. And since about 2000, we've kind of come to the they've estimated that we can actually have enough dose on a sample to actually beat this resolution limit. If we shoot it with a single shot with a just femtosecond beam, that's short enough. As I said, we need to look at outside the sample, so we need to have a high. We need to look at the higher angles. It needs to be a coherent wavefront, and the sample needs to be in the focus of the FEL. So I could show you and take you through iterative phase retrieval, but I actually kind of want to relate this to crystallography and how crystallography works, because a lot of X-ray scientists come from a crystallography background and may not fully appreciate how related they are. So let's say we have an object, and this is a plane illumination. So I just take a Fourier transform modulus squared to get the intensity. This is what the object looks like. It's a black object absorbing here, and it's a Bessel function. We know a circle makes a Bessel function. We shrink the object down. We actually, in the far field, the spacing gets bigger. We make the object smaller, the spacing gets even bigger. And you notice it actually no longer looks like a circle, and that's because of the pixelation I've been doing. This is actually no longer a circle. It's a little dot that is not quite a circle because of how small the pixels. And you notice I've been shifting the object next X and Y, but because the illumination is bigger than the object, it typically doesn't matter. It has a little shift, but it's a very small pointing. It really is on axis of the beam. Now we can make two objects, and you'll actually see this interesting characteristic pattern of two objects close to each other that's interfering with the two objects. We're going to make all sorts of arches or diffraction patterns, and we can sum them together. But they don't sum in intensity. They sum in, because they're coherently illuminated, those objects and that object, this object do not sum to make this one holistic object of a happy face. Yes, I am showing you a happy face diffraction pattern. And I can go from here. I can make two happy faces. I can make a row of happy faces. And you'll notice that the overall pattern doesn't change. It actually, the colors change and we make a nice lines, but the overall diffraction pattern doesn't change. It just gets these narrow bands. I can make patterns going this way. And at this point, I want to tell you that these patterns, they're line patterns. They relate to something, and you notice when I rotated, they actually, the rotation of the diffraction pattern is perpendicular to it. This relates to the most famous and important photo of X-ray photo that's probably ever been taken to date. And that was taken by Rosalind Franklin. This is photo 51, and it is of DNA. It's a DNA helix, and it is a fiber diffraction. And this pattern is a long twirled up DNA, and you end up with two stripes of the helical DNA. She would have won the Nobel Prize with Watson and Crick for this if she didn't pass away beforehand. And Watson and Crick owe a lot to her because they effectively stole this information. And one of her grad students showed them this picture before Rosalind even published and was still calculating it. So when Watson and Crick came up with their theory, Rosalind was coming up with this as well. And they actually published articles back to back in Nature. But this is probably the most famous X-ray photo taken. And it's a fiber diffraction, which, as I said, is just a row of objects that are repeating, like DNA strands. Now, I did promise we'll get back to crystallography. Here is a 3x3 object, and this is what the object looks like. It looks very similar to the happy face diffraction pattern, except you see these spots. And these spots are 81 times brighter than the single happy face. And that is just because it goes, the intensity goes as n squared. And of course, this is a small crystal. We can go to a bigger crystal. And you see only a smaller spots, the brighter, probably the resolution, you can't see spots out here, but they actually do exist. And you'll see this interesting stuff in between the spots. But these are the Bragg spots, and the intensity relates directly to the intensity of the single object, except it's sampled at the because of the crystal. And the weird information between these spots is related to the fact that I'm doing a finite crystal. I don't have an infinite one, so these spots would go away if it was infinite or would go really, really, really weak. But they actually exist, and that's important because this is one of the shortest papers I've ever seen written that actually has a pretty big impact. Some implications of Shannon's theorem by David Sayer. Claude Shannon was the father of information theory, and David Sayer was fairly famous in the field of crystallography and also in coherent refractive imaging. And pretty much what this paper is saying is if you just take the Bragg peaks, you can't actually have enough information to solve what the happy faces, actually individual happy faces, look like. You actually need the data in between each happy face. So in this case, I need all the intermediate spots. So I need about 4 times the data for here. And in real life, you need about 8 times data. You need to actually sample these intermediate values. This is called a phase problem. And there are solutions to actually how to get around the phase problem. It's also related to some iterative phase retrieval algorithms that we've developed. So as I said, crystallography and single particle imaging are very, very related, except single particle imaging in the object is much, much weaker. Crystallography, you get a boost from the fact that it's a crystal. Now you may say, well, why would I use this these toy happy faces? And the truth is, conceptually looking at these objects is important, especially for your conceptual understanding, because it can lead to actually some interesting places. This is actually from a paper that was published in a journal, where they actually took their ducks, got them all in a row, and got a nice crystal simulation from it, and they decided to actually move their ducks around a little bit, making them not so good, and you end up with Bragg peaks termination, where you end up with Bragg peaks turning off, and you end up with a coherent diffractive image at high Q that is related to the single duck, but instead of going as intensity squared or number of ducks squared, it goes only as the number of ducks. And they actually see this in crystals. Turns out this actually doesn't work with rotations very well, so you have a very small angular range. But for very weak bonds that are on a grid, like a crystal, sometimes you get Bragg termination where the crystal doesn't diffract very well for various reasons. One of those reasons could be that the the crystal is not perfect, and then you actually can get this. And we've seen this at LCLS. And this was one Henry Chapman Kartik Iyer came up with this method, and has been successfully used here to increase resolution beyond the Bragg limit, or the Bragg peak limit, I should say. So how do we, in single particle imaging, get the objects into the beam? This is a schematic that's been tossed around. We have a particle stream. They're in random orientations. We collect the diffraction pattern. We monitor the beam with a beam stop downstream of it, but we collect all this high Q scattering in the hopes of getting to atomic resolution. And this is what it looks like in practice, not just this theoretical image, but we actually have like real mirrors. In this case, grazing angle Kirkpatrick Baez mirrors that horizontally and vertically focus a beam. We have 120 hertz pulses. We have slits, different slit pairs, a particle stream of an aerosol source. Typically, we look at viruses because they're easy to make and to reproduce. And when we're testing this, and this is what the diffraction pattern actually looks like. We typically get 1, sometimes 2 objects in the beam, because our beam, we find making a 1 or 2 micron beam. To look at 70 nanometer objects means we have a higher hit rates. Making the beam smaller makes life a lot harder to actually image, especially since our aerosol focus is typically 100 microns. We keep it a little bit large because if we try to make it smaller, we have a lot of helium background or gas scattering background, which adds to the background noise, which is not so good. This is what this chamber looked like. This was the AMO hutch before it's now turned into TMO. The FEL comes from left to right. We have the detectors behind a gate valve. These were PNCCDs. We have GDVN electrospray feeding a aerodynamic lens stack, which is just a series of tubes, and the pressure differential focuses the gas and focuses the particles. We have a catching tube to make sure the particles don't bounce around the chamber, the slits and the forward jaws to make sure we have a clean beam, and we limit the scattering to areas just around the sample, which is important for this method. We really want to make sure we have a clean signal for orientation of the two-dimensional diffraction patterns in the three-dimensional space. This is when we first started in 2015, and this is what we get nowadays. The 3D reconstruction, we got down to sub-7 nanometers in the 6 nanometer range, and you can see data out to 2.6 nanometers very easily. In fact, we've seen data out to sub-nanometer in the 6 angstrom regime. This is PR772 bacteriophage. For the 3D reconstructions here, they look fairly close to the cryo-EM, although cryo-EM, as I said, has a higher resolution when it comes to actually getting a single object. They actually sum over multiple objects, just as we do, to actually get to actually increase the resolution. So this is encouraging, but it's nowhere near the cryo-EM resolution, but it still beats the 10 nanometer limit what you can do with standard cryo-cooled samples at synchrotrons. For more details, please see the references. And that brings us to LCLS2. And as I said, we ended up getting about 7 nanometer resolution on a 70 nanometer object. And to be honest, that's kind of what we should expect based on 1 millijoule pulses. If we had 6 nanometers, we expect from a SLAC's point of view, we expect we need 100 to 1,000 images with no noise, no noise, and to get to that 2 nanometer regime, or 2.6 nanometers, we would need 10,000 images, which is quite a lot of data. And at 120 hertz, that takes multiple shifts of everything aligned and just collecting data and not changing anything except adding more sample. But we now have LCLS2 coming up online, where we get thousands of pulses and actually get image 5 to 10,000 pulses per second, or so 5 or 10 kilohertz. And now this problem becomes tractable within a few hours, if not, and maybe even allows us to see actually dynamics. By the way, if you want to know how to do the modeling, it's fairly straightforward. There's a wonderful paper that came out a few years ago to actually show you exactly how much data you need to do this technique. And this is what European XFAL did. This is little gold objects, 30 nanometer, 40 nanometer cube, and 17 nanometer cubes. And they collected 15 million frames of data on some of these. And they were able to construct the three-dimensional diffraction volume and reconstruct the three-dimensional what the objects actually look like. Now, gold's a little cheating, as I'll show, mostly because well, if you look at biological stuff, these objects are much more dense, have a higher scattering rates, but that's still pretty impressive. It still is the best. This 2 nanometer resolution is still the best when it comes to what's been achieved. We've, as I said, on the biological front, it gone down to about 6, which is similar to what the octagon resolution was for larger octagons, and we were just very limited by the amount of data we can collect. I love this picture from what they published, and you actually see they broke the data down to 71 arbitrary categories, so they actually try to see if they can see any changes. Some of these were just junk. Some of these, like this frame here, is quite clearly one of these 2 objects stuck together, and you can see that based on the fraction of this that I showed you earlier, or the modeling I showed you earlier. The happy faces is just 2 objects stuck together, which is kind of neat that they actually see this and they actually can sort the data. So we can think about actually sorting the data on a reaction coordinate where we actually see motion, and that's something that with a high repetition rate, we will be able to do. So as I said, I'm in charge of the tender X-ray instrument. The tender X-ray instrument actually can take beam from the soft X-ray angulator as well as a hard X-ray angulator, and we can do this simultaneously if we wanted to, and we will probably for certain experiments where we're going to do X-ray pump, X-ray probe. We have 2 profile monitors in the front of Hutch 1.2, followed by a set of Kirkpatrick-Baez mirrors focusing optics, which focus on the Hutch. We have a laser table for laser pumped experiments. And we have roll in, roll out end stations. So we have a planned forward scattering high vacuum UHV, actually high vacuum HV chamber that can roll in and roll out, and a spectrometry chamber, and plans for a future nonlinear chamber coming in. We have a primary forward scattering detector, which will collect these diffraction patterns. And we have diagnostics. These turn out to be very critical when you're using sub-micron beams. These are wavefront sensors and power meters to actually tell you what intensity is coming down the pipe, and make sure your focus is stable and the same day-to-day, hour-to-hour, which does tend to change with all the parameters of the LCLS changing. We have arrival time monitors for laser, differential pumping, because we have to actually go from a dirty aerosol environment to 10 to minus 9 vacuum in a really short distance. We really need to have, we pretty much compact as much space as we can to make us focus just below 1 micron, and that limited us exactly how much space we had to actually do all of our upstream diagnostics. But we were able to squeeze in a differential pump, an arrival time monitor, and a laser uncoupling all in one small location that's about 1 meter long. We also squeeze in a low Q detector to pretty much, we minimize this distance between the diagnostic table and the low Q detector. So this is just valid enough to allow us to walk underneath the beam without actually having a to have a permit for confined spaces every single time we want to access our racks in the back of or access anything in the back of the hutch. So this is pushes a small detector as far back as possible, so we can actually get low Q and grazing angle scattering, which is very useful for certain experiments. Parameters, this is a tender X-ray instrument, and it covers a tender range, which I usually define from the silicon K edge, which is 1.8 kV, up to the iron edge, which is about just around 7 kV. On the soft X-ray side, we go from about 2.5 to 5 kV, and on the hard X-ray side, we go from about 1, which is the limit of what the undulator can do, to about 7.5 kV, limited by our optics we chose and the coatings on the optics. We have a delay line, which can cover that range from about 2.1 kV, because that's where silicon 111 turns on and back reflection, up until the limit of our optics. Typically, we can the optics can actually sustain high power loads up to 200 watts, which means we can have a lot of high repetition rate beam, or 40 watts when we're using a monochromatic beam. As I said, our optics were designed to be about 1 micron and be able to overbend the mirrors a little bit to get about 10 micron spot if we want to work out a focus. And we've really tried when it comes to designing our optical mounts, to get really high stability by choosing and how we design our KB, our focusing mirrors, and how we think about doing time stability for X-ray pump X-ray probe measurements. We're thinking about some really interesting ideas of how to actually get very good time stability. But this is about forward scattering, which is one of the 3 techniques that TXI is focusing on. And we actually had a lot of questions when it comes to actually designing instruments and hardware. For example, what's the best photon energy for this technique? How many photons do you need? How much data do you want to collect? How long the X-ray pulses should be? And what are the other current limiting factors in this type of forward scattering experiment? And are there any other types of samples besides biology that's interesting? And the answer to all these had to be addressed before you start designing instruments. And we'll go over a couple of them. For example, we chose 3 to 4 kV because the scattering, and this is the limit of what you want to. 4 kV gets you in the Angstrom regime, where you actually are getting atomic information in a forward direction. But we've done this experiment before, where we actually take these little nano Ks made out of plastic, PMMA plastic, and we take them at CXI, and we actually scan them at 5 kV, and we did the same exact experiment at 10 kV. And while we couldn't photon count at 5 kV, we could photon count at 10 kV. You can see the fraction quality is a lot better. And the reason for this actually is that at 5 kV, for every millijoule of pulse energy, you end up with twice as many photons. So our signal noise is square root of 2 better. And since the real part, or the scattering part of the atomic scattering factors for carbon above a kilovolt doesn't change as you go up until you get to Thompson's Compton scattering. The Thompson regime, it doesn't change. Going to the lower photon energy, if it gets you higher millijoules, or same millijoules, gets you more photons scattered on the detector, which means you get a better signal noise. Transmission doesn't seem to be a problem. This is the imaginary part. Because these are very small samples, we can transmit through them very easily. So we went through this exercise where we actually looked at every single parameter such as this, and we modeled it as best we could. And this is why we chose the photon energy ranges we chose. We chose the KBs to maximize stability and to get the focus as close to interaction point as possible, making the focus as small as possible with the mirror technology we had, which is meter-long mirrors. Vertical focusing and then horizontal focusing. They're all on one large piece of granite. So when we do X-ray pump X-ray probe, if the granite moves around, the beam doesn't move. The overlap will the beam will move, but the 2 overlap spots will move together. We chose boron carbide and nickel coatings because those seem not to melt in the front end enclosure, which is important, and they give us nice high reflectivities. Kirkpatrick Baez mirrors, by the way, are just grazing angled mirrors. Because the index refraction is less than 1, you end up in a regime where if you're really great grazing angles, you get total external reflection, which gives you almost a perfect, in this case, like boron carbide, 90% plus over 90% reflectivity over a large bandwidth, which means these are achromatic systems, which means you just don't focus on like crystals where you focus on 1 photon energy, or beryllium lenses where you have chromatic aberrations, we actually make really small foci very nicely and cleanly. So we chose this technology for that reason. It also works over the very broad range of photon energies that TXI can serve. So this is what, and a lot of care went into figuring out these parameters. This is what the system looks like. It just showed up. This was when it was bubble wrapped a few months ago, and we're starting to install the mirrors and getting all the mechanics working for when TXI turns on next year. Another aspect of the that we focus on is the detector. When you're doing forward scattering, not only do you want to have a really nice, high quality focus, but you need to actually make sure that these detectors in the right place with and can read out at the high repetition rates we need. So we have a large detector that can move from really close to the focus, about a little bit bigger than 5 centimeters away, to half a meter away. And we have a variable gap. We have the gap because we have the two beams crossing, so we actually don't want to melt any pixels when we actually move the detector all the way back. So we have a gap for the detectors, which is covered by the low Q detector, which can move back and forth between the two beams, collecting a lot of low Q scattering and diffraction. You'll notice the detector is tiled, and this has to do because to read out at these high repetition rates, you need a lot of electronics, and you need a lot of readouts. And the only way to do that was to tile at this point, unless we change how these detectors are actually built, which is high risk. So this will start at 5 kilohertz, with each of these little tiles being 144 by 192 pixels. And we can go up to, eventually we have a path to 10 kilohertz, and then we have some ideas for technology that's coming in down the pipeline to be in the 25 kilohertz regime. We specifically tailored this detector to read photons and count single photons around 2 keV up, and be optimized to detect up to 10,000 photons per pixel at 4 keV. As I said, this is either 100 micron pixels, so they're relatively relatively the same size as what we typically use here at the facility. So the distances you typically put a detector are kept about the same. Now, TXI, as I said, is a multidisciplinary instrument with roll-in-roll-out end stations. First up, we are going to be probably doing tender spectroscopy. This is sulfur, phosphor, and other interesting calcium and other interesting biological elements. And we can do laser pumping in chemistry and see how these molecules move and really record what's going on with them. Other aspects, since we have two beams, we can think about doing nonlinear spectroscopies, or pumping a system with a soft X-ray and doing transient diffraction and looking at how actually systems react when only one species of atoms are absorbing and in diffraction. But what's more interesting to me is what I call multidimensional probe spectroscopies, where we're looking at, for example, nanocatalytic particles with some organics on them. And if they're all identical particles, we can actually collect on the soft X-ray line a spectrum, either photoelectron spectrum or X-ray spectrum at carbon, oxygen, nitrogen. And in the hard X-ray line, we can do diffraction. And now you have all the diffraction data. You can actually sort either on the spectrum, a few photons on the spectral data, or sort on your diffraction data. And if all the particles are the same, your spectral data is going to give you a natural time coordinate of the reaction. And then you can actually correlate what's going on the surface of this nanocatalytic particle as a function of time, which is really, really cool, where you're not really triggering, but you're collecting enough data and useful data and different dimensionalities to actually record what's going on in time without a time axis. And these type of two beam experiments can only be done at TXI because we can combine X-rays at two vastly different photon energies at the same time. And with that, I'd like to thank the team. The single particle imaging collaboration here was going for about 5 years. I was in charge of it, and we've learned a lot about actually how to actually put biological and other particles in the beam, and actually how to collect data over the course of that time, really getting some really impressive results. The TXI team, with our engineering staff and our area staff to make sure everything gets installed, and Roberto is in charge of the spectroscopy aspect of the TXI. They've been really helpful. And with that, thank you very much, and I hope you really enjoy the rest of the user meeting. And if you ever need anything, feel free to email me your questions, and I'll be happy to answer them. Thank you.